I wanted to make this video about Archimedes Principle, but it really is part 2 of a series. Make sure you look at the video on buoyant force first. Well, in that video, we talked about the fact that as an object is submerged in a fluid, the deeper you go, the more pressure there is, but there's always going to be more pressure against the bottom of an object than the top because the bottom is always deeper. And that explains why there's a buoyant force. But to be able to calculate the magnitude of the buoyant force, it is surprisingly as simple as the buoyant force equals the weight of the fluid displaced. So whatever fluid got pushed out of the way because of the object, the weight of that fluid is exactly equal to the buoyant force. And when something is floating, and this is just an application of Newton's second law, that if it's not accelerating, the force up and the force down, or the total forces, equal 0. So when something is floating, the upward force due to buoyancy must equal the downward force due to the weight of the object. And because the buoyant force is the same thing as the weight of the fluid has to equal the weight of the object itself, because that's equal to the buoyant force, equals the weight of the object. And there's lots of misconceptions about buoyancy, so I wanted to introduce one that I saw in a children's book. But it says, things float because the water pushes up on them more than they push down on the water. I hope you recognize that as a complete violation of Newton's third law, action-reaction. The water can't push up on the object more than the object pushes on the water because it's an action-reaction pair. But another example, or before we move on, I want to just clarify two situations. When something is floating, we just said that the net force on it is 0, so gravity pulling down on that beach ball is exactly equal to the water pushing up. So when something is floating, the weight of that object and the weight of the fluid displaced, that little sliver of water that got pushed out of the way, those two must have equal weights. But when something is submerged, the volume of that object, how big, how many cubic centimeters it is, has to equal the volume of the water displaced. So when it is submerged, they have equal volumes, even though they could very much have different weights. The billiard ball sank to the bottom because it weighed more than the buoyant force, or the weight of the water displaced. Some interesting applications of this is here is a bridge for boats, and if that bridge had a big old bathroom scale underneath it, and pretend there were no boats on that bridge, just the water, and a boat came sailing over the top of that, what do you think? Do you think the bathroom scale would read more as that boat passed over the top, loaded with people and stuff? Or would it weigh the same, or would it weigh less? All right, now that you've had a chance to think about that, the answer is it's going to be the same. And that is because when the boat is floating, the weight of that boat has to exactly equal to the weight of the water displaced. So the water that's not there because of the boat is equal to the weight of the boat. And it just balances itself out. An interesting example of that, or an application, is this. It's called the Falkirk wheel. This this canal comes here, and there's a difference in height from this canal. And it used to be that there were different locks, where like bathtubs, where you'd fill up the water, the boat would raise and fall. But the boat goes in here in a giant tub. Another boat could go in there, and it just rotates around under the power of a motor. But the motor doesn't have to be that powerful because it's exactly balanced. And it doesn't matter if a boat is in this bathtub or not. If the water in that tub is filled right to that level there and spilled over, it wouldn't matter if there was a boat there or not, because again, the weight of the boat equals the weight of the water that got displaced, the buoyant force. All right, some other interesting examples. In the first video, I talked about the fact that if an object is submerged, there's pressure all the way around. The pressure on the left pushing that way and the pressure on the right pushing that way are balanced out, but there's going to be always more pressure against the bottom than the top, because the deeper you go, the more pressure there is. And I use that example to say, because this is a linear relationship, the difference in pressure from top to bottom here will have the same difference in pressure from top to bottom here. So the buoyant force on this is the same as the buoyant force on that. The buoyant force is going to be the same at all depths. And the buoyant force decreases with depth. And you think, how can both of those be true? Well, they're both true in their own situation. Here is a situation where the buoyant force got less the deeper it went. And that's because in this example over here, the object was solid and could not compress. It wasn't crushable. Here, the styrofoam head was taken down to 2,000 feet and 6,000 and 9,000 feet, and that fantastic amount of pressure crushed it into a smaller volume. And that smaller volume displaced less water, so the buoyant force was less. Now, you may have known for a long time and been able to say that an object that is more dense than the fluid it is in sinks, while an object that is less dense floats. And that is true, but do you understand why? Could you articulate the reason that that is true? Well, the real question is, why is that true? Why does an object that is more dense than the fluid is in sink, and while an object that is less dense than the fluid is in floats? That's the real question. Let's see if we can explain it this way. If all of these were 1 liter, 10 centimeters by 10 centimeters by 10 centimeters, if it was made out of balsa wood, it would only have a mass of 0.12 kilograms. Pine, 0.5, granite, 2.75, steel, 7.8 kilograms, and we know that water has a mass of 1 kilogram per liter. So gravity is pulling down on this with a lot of force, and then the balsa wood doesn't weigh very much, so there's very little force. But if I submerged all of those, submerged completely under the water, this much balsa wood is going to displace this much water, and same for all those. So the buoyant force is equal to the weight of the fluid displaced. This displaces a kilogram of water, which weighs 9.8 newtons. So the buoyant force on all of these is 9.8 newtons. Here, the buoyant force was greater than what it weighed, so there was a net force up. And for these two, the buoyant force was less than what it weighed, so there was a net force down. This chunk of water in water would be neutrally buoyant. So if I had pine that would, when it's completely submerged, submerges a full liter of water. So the buoyant force would be 9.8 newtons, and then it would only weigh half that. So if you let that thing shoot to the surface and float, it only has to displace 4.9 newtons or 0.5 kilograms of water to be able to have the buoyant force equal to the weight of the balsa wood itself, because this much water weighs just as much as that much pine wood. I said balsa earlier. So if you have this submerged in fluid, there's this really big buoyant force up, the gravity's pulling down about half as much, and there is a net force in the up direction, which means it will accelerate in the up direction. When it busts through the water here and doesn't displace as much water, it will shoot up until the net force is 0, where the buoyant force equals the weight of the object. Here's a fun fact. If you take diet sodas or regular sodas and submerge them all in a fluid like water, invariably the diet ones will float to the surface and the regulars will sink, And that is because sugar is not very sweet. And you think, that's the explanation? Well, it takes a lot of sugar to make something sweet. You have to add like 40 grams of sugar or so to get that sweet enough. If this is an artificial sweetener, you have to just add a tiny amount of extra of sweetener to get it sweet enough. So this has a lot of solid material dissolved into it. This has just a little bit of solid material dissolved into it, and that makes that more dense than water, and this is less dense than water. And you may have observed this if you ever went to a picnic or a fair for school or something like that. But you may have thought it was a conspiracy from the teachers that they put all the diet stuff on the top there while you had to really dig through that ice bucket to get the good stuff. Another interesting fact is that mercury is a liquid. You don't get to play with it very much anymore, but I certainly remember as a kid being able to play with mercury. And it is very, very dense. It's hard to wrap your brain around the fact that how dense it really is. If you tried to pick up a container of mercury, it just seems way heavier than something that big could possibly be. But if this is a liter of mercury, it would have a mass of about 13.5 kilograms, that same volume of steel, only about 7.8 kilograms. So gravity's pulling down on that with more force than gravity's pulling down on that. And if you took a chunk of steel like that and submerged it in a big vat of mercury, well, this much steel is going to displace that much mercury. So the buoyant force is equal to the weight of the fluid displaced. There'd be a net force up, and I'm saying it's 5.7 kilograms. Remember, we have to multiply by 9.8 to get it into newtons. But steel will float on mercury. A billiard ball in a mug of mercury. Don't drink the stuff. But this little sliver of mercury that is displacing weighs as much as the entire ball there. Okay, so we might recognize North America here and the Great Lakes, and ships that sail from saltwater here down the St. Lawrence River into the freshwater. They have to be careful, because if that ship is floating along like that and it's loaded down, remember, the weight of the ship has to equal the weight of the water it's displacing. If that ship goes from salt water, which is real dense or more dense, into fresh water, which is less dense, and it stays the same load, it has to displace the same weight of water here versus here. But because fresh water is less dense, it would have to displace a greater volume of fresh water to get the same weight as that volume of salt water. So what's going to happen is that boat's going to have to sink deeper, and maybe not quite as much as I've shown in the animation here. I'm sure not nearly that. Okay, another fun example is with kayaks. Now, a plastic kayak like that, the weight of the boat and the person could weigh about 200 pounds. And this is a wood sea kayak, but the boat and person could also weigh 200 pounds. So in order for them to float, they have to displace 200 pounds of water. And remember that 1 gallon is 8.3 pounds. So they have to displace about 24 gallons of water. But the shape of that water displaced has a lot to do with the performance of that boat. This boat is going to displace a very short distance in length and a lot of distance, or more distance in depth. And this is going to displace that volume of 24 gallons in length and very little depth. So looking at it edgewise here, this boat has to push all this water out of the way to move through the water. And this one here is going to sit very shallow in the water. So if you're going to race the boat and you want to be very efficient, you want it super, super long, displacing its volume of water in length and very, very, very little depth. When you sail and the wind makes the boat tip like this, it's called heeling. And when the boat heels over like this, the boat is actually more efficient at sliding through the water. So when the boat tips over like this, when the boat's sitting upright, it's just kind of this straight water line, and it goes from here to here. That's where it goes from above water to under the water. When the boat tips over, the length of the water line increases, so the depth that it goes down decreases. So you're displacing more volume in length and not so much in depth, so it's easier to move through the water. A PFD, a personal flotation device. You might think, how does it work? How does it make you more buoyant? Well, it just adds to your volume without adding a lot of weight. So when you are in water, you displace more water than you would otherwise. You'd have to sink deeper without a life jacket. And if you wear a wetsuit, scuba diving or something, this increases your volume a lot without increasing your weight a lot. So you have to add lead weights to even sink under the water. Icebergs, you've heard the phrase tip of the iceberg. And when we have this iceberg like this, the majority of the ice is under the water. But the question you might think about the question, what would happen if that ice melted? Would it make the sea rise or fall or stay the same? So let's think about that. In terms of buoyancy, the weight of all that ice right here takes up this volume. But because it's floating, the weight of that ice has to equal the weight of the water it's displacing. So all that water that got displaced is equal in weight to the weight of all that ice. Now, what happens when that ice melts? Is the water out here going to rise or fall or stay the same? Well, the weight of that ice and the weight of the water has to equal, so the masses must equal. Mass is the same thing as density times volume. So the ice had a low density and a big volume. The water had a larger density and had a smaller volume. When the ice melts and becomes liquid water, the density of the ice becomes the density of the water. So the volume of the ice becomes the volume of the water. And so the sea would neither rise nor fall. Well, here's the question. Which ice would contribute to rising sea levels? Sea ice or land ice? And so this is ice that was on the land and then melted into the water, or ice that is in the water and just melted into the water. This would not contribute to sea level rise. This ice would, although it's not the biggest contributor to sea level rise. The biggest contributor to sea level rise is simply thermal expansion, that as the ocean warms up, it gets bigger and takes on more volume, called thermal expansion. All right, now think about this. If we had a swimming pool here and we marked the line where the water hit the edge of the swimming pool, and we had a little boat in there with a container of water, a big container of water, what do you think would happen to the water level if we took this container, dumped it out of the boat and into this water? Do you think the water is going to go down? Is it going to go up? Or is it going to stay the same? Now that you've had a chance to think about that, the answer is it will stay the same. And that again comes from the fact that because this is floating, the water that got pushed to the side from that boat being there, displaced, equals the weight of all that stuff. So when you take weight out of the boat rises up, and because the weights are the same, the volumes are the same. A lava lamp is kind of a cool toy here, but there's a little heating element down here. This is like a waxy kind of material that when it heats up, it expands and will become more buoyant, float to the top. It cools, and as it cools, it contracts, so it becomes less buoyant and sinks to the bottom. And then a Galilean thermometer is going to be the exact opposite, where these little bulbs are made out of glass and they don't change their volume very much. The liquid that they're submerged in is more sensitive to changes in volume with changes in temperature. So as this warms up, this fluid here warms up, it becomes less dense. So the fluid that this is displacing won't weigh as much, and the buoyant force will decrease. And these are weighted so it just crosses over and drops as the buoyant force decreased. You read the temperature by the lowest tag there, still floating. And then this big old ship here, you think, how can that float? Well, if we look at it, there is a lot of boat being displacing water under the waterline. And there's another ship in dry dock. But those are just a few examples of buoyancy, and I hope you enjoyed.